Hello everyone. As you know, the path planning was really a non-parametric identification of the path, right? Basically, what you did, you determined a bunch of waypoints and you tried to go from one waypoint to another and avoid collision. But you never specified in path planning that when you have Q values, correct, for each one of the waypoints, you have not specified how the Q, the joint variables, would change as a function of time from one waypoint to another, right? So all you have was the endpoints, just the endpoint Q, Q1, and Q2, or Q0 and Q final. That's all you had. How Q changes versus time, that was not discussed in path planning, and that is the topic of trajectory generation. So in trajectory generation, I want to find Q as a function of time. What kind of time function I should choose for Q if I only know the endpoints. And you might say, why is that any important? Because if I am sure that there is no collision happening, what's the importance of Q? Well, you know, if for example Q corresponds to the angle of a joint, right? Let's say it's a rotary joint, then the time derivative of this Q is what? Q dot, which is the angular velocity, omega, and then what? The time derivative of that is Q double dot, which is the angular acceleration, or alpha, correct? And this angular acceleration does depend on what? On the torque, correct? For example, you know, if it's theta double dot or alpha is equal to what? The torque divided by the mass moment of inertia, I, right? Or if it's like it's a prismatic joint, then d double dot is equal to the force applied to the joint divided by the mass, correct? And you know you have physical limitations on the amount of the torque that a motor can generate or the force that a linear actuator can generate, right? They have limitations, and so when you divide them by these numbers, I or M, your D or your theta double dots, they have some max values, correct? Right? So if I want to write it like this, you have some maximum. This is like A, correct? This is like A and this is like alpha. There is some maximum acceleration and maximum what? Linear or angular acceleration you can have, and also when you integrate those, this guy can be either linear velocity or what? Angular velocity. This guy will only also have some maximum, correct? You cannot expect from a motor to give you any RPM that you want and any torque that you want. And you also know that the omega and torque, for example, for a motor, they do depend on each other, right? As the RPM goes up, the torque drops and vice versa. So you have limitations, physical limitations on the driving force or the driving torque behind your joint. And that's why this function of Q does matter. Because if you choose this Q of t such that your angular acceleration or linear acceleration exceeds what the motor can give you, then your robot cannot achieve the task, right, the way that you want. For example, let's say I want to go from my initial Q value, and let's say T naught is 0 or whatever, and TF is 2 seconds. And I want to go from initial Q of 0 radians to final Q of, let's say, 400 radians. And the timing I have is from 0 to 2 seconds. So in 2 seconds, your joint has to rotate 400 radians, which is on average 200 radians per second. And if you multiply that by 60 over 2 pi, correct? You can convert it into RPM. 60 over 2 pi is roughly 10. So 200 RPM means what? Means 200 radians per second means 2000 RPM. Now, can your motor give you such RPM? Maybe, maybe not. And also when you calculate your acceleration, I'll show you angular acceleration, maybe it shows that your maximum angular acceleration based on the inertia of the motor is going to be, and the load, of course, right? This is the inertia equivalent. This torque is going to be, let's say, 100 Newton meters. Does your motor have that torque? Maybe, maybe not. So you have to know how these joint variables are changing versus time. Good. So now that we know the importance of it, how do we determine that? So there are different ways depending on what is it that you want to control and what is it that you have, what pieces of information you have. Then there are different methods. What are the limitations and so on? There are different methods for generating trajectories. Here we discussed two of them that are polynomial, cubic and quintic. And then there is one that is very common in robotics application, trapezoidal motion profile, or you might also call it linear segment with parabolic blend. Okay, so in terms of joint angle, it's parabola line parabola. In terms of velocity, it's a trapezoidal. Okay, and then finally we look at the S curve, which is a trapezoidal, but it is smooth. So here we need to look at a bunch of things. The last thing I want to talk about before we start is the notion of jerk. Okay, this jerk is a physical quantity, and it is defined as time derivative of the acceleration. Okay, so for example, if it's theta double dot, jerk is like the time derivative of theta double dot. If it's a, it's like the derivative of a. So the rate of change of acceleration, whether it's linear or angular, doesn't matter. The rate of change of that, we call it jerk. And what does this one show really physically? As the name says, it's the jerk in the motion. So if you ride, for example, in a taxi, and the taxi, what? Does have sudden stops, slams on the brake, and then when he starts moving, he slams on the accelerator, right? So if you look at the acceleration plot versus time, right? Let's say first the taxi is cruising, so acceleration is 0, then he boom, slams on the brake, and in a very short time, he goes to a very big negative acceleration. Right, and then what? He goes to 0 speed, and then stays there stationary for some time. Then when he wants to start moving again, boom, slams on the accelerator and goes to a huge acceleration again. Right, so if you look at this type of motion when you are sitting in the car, you feel all of these changes in acceleration, which is basically the changes in the forces applied to your body. And if the forces that are applied to your body from the seats of the taxi, you're not going to feel any comfortable, right? You see, one time the seat is pushing you, the other time you are going to the windshield, and so on and so forth, right? So that's what you felt. Or like when you go to these different rides in a theme park, you see when the merry-go-round or anything like that is rotating this way, and all of a sudden they what? They stop and they switch the direction of rotation. Or it goes right. Some of these rides, if you have seen, they go, when they are also rotating, they also go what? Up and down, and those changes in acceleration or the changes in the force will cause the jerk in the motion, okay? So this idea of jerk, just wanted you to know about it because that is important to us. So now let's talk about the polynomial functions for the trajectory, right? Cubic and quintic. So when is it that cubic polynomial is a good function to choose? when you only have 4 values that you necessarily want to achieve. What are they? It's the joint variable at the beginning time, it's the joint variable at the final time, and then the joint velocity at the beginning and the final time. Right? So all you know are the joint values at the beginning, at the end, and the joint velocities at the beginning and at the end. And here we are just focusing on one variable. So here Q is not a vector, it's just one variable. But you can do this operation, you can do this basically curve fitting, right, to each and every one of the joint variables, right? So if you have 4 joints, and you call them Q1, Q2, 3, and 4. For each one of those Q's, you can apply a cubic polynomial like this. So I say now this specific Q is going to be a cubic polynomial. So it has 4 coefficients unknown, A0, A1, A2, and A3. And this guy is going to satisfy these 4 conditions for me. Why? Because it has 4 unknowns. Correct? So we set it equal to this, and then we apply these conditions. So for t, we apply t0 and set it equal to q at t0. Then for t again, we apply tf, and it is going to be q at tf. Then we take a time derivative from this, and in that time derivative, q dot, which is what? Clearly, you know, q dot is going to be a1 plus 2a2 t plus 3a3 t squared. In that one, again, you plug in t0 and t final, and the values for them, you call them q dot at t0 and q dot at tf. And you will get 4 equations. Here are these 4 equations arranged in a matrix format, where here, this matrix on the left-hand side, this A matrix is a matrix with known values. Everything depends on time. This is your unknown vector x, which are the unknown coefficients, and the right-hand side is also a known vector based on the 4 given values. So clearly from here, your unknown vector x is going to be what? A inverse times b, and once you have that, you plug them back here. You have now your q as a function of time. So you made your q values parametric. What is the parameter? It is time. Okay, and if you look at the way that the function is, so at time t0, it is q0. Q0 is this guy. This is called q0. And t final, it is q final. And also the slopes at the beginning, this initial slope here, this initial slope, if you call this angle, for example, alpha, let's see if I can do. So here, that's the initial slope. And this angle is alpha. Clearly, alpha is tangent inverse of q dot at t0. And then you also have some final slope like this. And again, the angle of that with respect to the positive horizontal axis beta, this is equal to tangent inverse of q dot at t final. Okay, so you have the initial and final slope and initial and final value, and it passes a cubic polynomial. This is what you see. And then, as I said, you can plot your q dot, which is like this with the coefficients that you determined. And you can also determine your what? Q double dot, the acceleration terms, which is going to be 2a2 plus 6a3 times t. Okay, and so here I'm going to show you that in a MATLAB demo. So these values I chosen is my initial time. I chose it to be 0.5, final time 4.5. I go from pi over 6 to 4 pi over 6. So all I'm rotating is about 180 degrees. I'm rotating 180 degrees in 4 seconds. It's not such a big deal. And my initial and final slopes are given as 0.5 and 0.2. I calculate my A, and right hand side here is the same as B matrix. Get my coefficients. get my q dot, q double dot, and all I'm doing is plotting it, right? So here we go. You can see q dot, and q double dot, all of them as a function of time. Clearly, you see your q starts at pi over 6, right, at 30 degrees, and goes to 7 pi over 6, correct, which is 210. So you can see that's 210 in radians, of course. This is 30 degrees, or pi over 6. You know, pi is a little bit more bigger than 3, so over 6 means more than half. And clearly, you see this number here is a little bit more than half. And you have some initial slope of 0.5, and you have some final slope of 0.2. There is a positive slope both in the beginning and at the end, correct? You can easily draw a tangent line like this, and one like that. And look that in the beginning and at the end there are some slopes. Not a big slope, but there is definitely one involved. And now if you look at q dot and q double dot, you see your maximum q dot is what? 1 radians per second. And your maximum q double dot in magnitude, it is here, which is somewhere like 0.72, 0.73 or so. Okay, so now can you have this much of angular acceleration or linear acceleration? Well, it depends on your motor, right? Whether your motor can do that or not. Now, to show you the effect of what can change to the maximum q dot and q double dot, I'll try to make it a little bit faster. I say in only 1 second, try to go 180 degrees, or maybe, you know what? Let's make it 360 degrees. So go one full rotation is in about 1 second, and the initial slope, final slope are good. So let me run it one more time. Now look. So all I did, instead of 4 seconds, I made it 1 second, and I made the amount of rotation 2 times larger. Now you clearly see again, you are going from pi over 6 to 13 pi over 6, which is 390 degrees. But now look at your max value of theta dot, the max angular velocity. Now it is 9.25 radians per second. If you multiply it by 10, it is about 92, 93 RPMs. Is that achievable? Most probably yes, for most motors. What about angular acceleration? Now, if you look at the max value is around what? It is 35.3 radians per second squared. If you multiply that by the inertia equivalent of the motor, can the motor torque will provide such amount of angular acceleration? Maybe, okay? So we can look at one simple motor here with some specs, right? See what is the Tmax and what is I for it, and what is theta dot, correct? And as I said, this omega and this guy times I, which is torque, these two are not just independent from each other. If you want, you can have a fourth plot, really, and you can consider some I equivalent, right? So we come up with a number, then we multiply our Q2 dot by some I and call it torque. So torque is I equivalent times Q2 dot. Now here, since I'm interested in the maximum torque that the motion needs, I'm going to get the maximum angular acceleration and multiply it by the I equivalent and call it maximum torque, and we'll show it on in the command window. I would also convert my maximum omega into RPM, so multiply it by 60 divided by 2 pi, and 60 divided by 2 is 30, so multiply by 30 divided by pi. So this is max omega in RPM, and this is max torque in Newton meters. And if you know from motors, if you have a gearbox after the motor with a speed reduction with factor n. Let's say here the factor is 16. So the gearbox reduces the RPM by 16 times. And if you have the I of the shaft of the motor to be a very small number typically, and then I of the load, then the equivalent is going to be the I of the motor plus the I of the load divided by the reduction factor squared. So here I calculate that, and then I plot this. Here I also made my final angle to be quite bigger. So instead of going 1 full round, now it is going 5 full rounds, okay? And 5 is basically 61 divided by 12, because in each full round you have 12 30 degrees, and this is 61 times that, and the first one is 1 times that, so the difference is 60 times 30 degrees, which is 5 times 360. So it is doing 5 full revolutions in 1 second with these numbers for the inertia of the shaft, the load, the gear reduction, and everything. And if I run this to get my plots, now if I go and look at the values for maximum RPM, it is 448 RPM, and max torque is 1.07 Newton meters, right? Now if I go, for example, and search a specific DC motor, right, then I get this kind of curve. As I said, the RPM increases, the torque drops, and vice versa. And now if I look at the maximum torque, which we call the stall torque for this, let's say DC motor, it is something like 0.32, 0.33 Newtons meter, while here you can see 1.07, which is like 3 times bigger or more. So definitely, if I want to achieve this motion, it's not going to be possible, right? It is not going to be possible. So I have to change this Q as a function of time, right? Or I have to choose a different motor that is more powerful, or bump up the voltage of the motor. So clearly you see this function of time. Q as a function of time determines Q double dot, when multiplied by I equivalent determines torque max, and torque max determines whether you can go with the motor that you have or you have to change it. So the choice of the time function in this trajectory generation is very, very important. Okay, now it is time to look at quintic or fifth order polynomials. So last time we saw that we chose cubic with 4 unknown coefficients because we were given 4 numbers that our polynomial should satisfy: the initial and final joint values and the initial and final speed values. Now, if we also have to satisfy the initial and the final acceleration values, Q double dots, then we definitely need 6 coefficients, and that comes from a fifth order polynomial like this. And again, the unknowns from A0 to A5 can easily be found using a matrix format, right? Where here you have a coefficient of known values, the coefficient matrix here, which is all based on the time, T0 and T final. So this is the known matrix A. Right-hand side is also the given numbers. And so by inverting this matrix, multiplying by the right-hand side, you can get your coefficients. And now if you look at, for example, position for a specific set of numbers, you see it is a fifth order. Now it might look like a cubic. It might, yes, depending on your initial and final Q and initial and final time. And then you have the velocity, which has some max velocity, and you have some acceleration, which has some, again, max and min values. So here I'll show you a demo of that. And I use the same numbers I used last time for cubic. So I go 5 full rounds in 1 second. And last time we had to satisfy the 2 initial and final speeds. This time we also have to satisfy the initial and the final accelerations, 0 and 0.1. And I also again calculate the maximum torque and the maximum speed and show them with fprintf. So if you remember when we did the cubic, with these numbers, right? I guess I ran the whole thing. When we did cubic, this is the chart that we got, and the numbers that we got were also here. I guess if you can see them, right? Let me clean up everything and do it one more time. So the max RPM was 448 and the max torque was 1.08 Newton meters. Now here I'm gonna do the quintic one, and this is how the plot would look like for the set of numbers that I provided. And now if you look, your maximum RPM is even less than the cubic one, but if you look, your maximum torque is way larger. Okay, so that's another thing that you have to consider, that the order of the polynomial, of course, it does depend on how many conditions you have to satisfy, but in general, it's not really a good idea to add to the orders of the polynomials when you do curve fitting. And you know, the problem there is called the overfitting problem, which will be discussed in a later video. But I guess if you go to my channel under the playlist Engineering Mathematics and look at the curve fitting video, where I talked about least squares curve fitting, you see over there when I talk about polynomials, I explain the problem of the issue of overfitting. Okay, so you can refer to that. In general, we try to use as small as a set of parameters that we can, minimal number of coefficients we can to satisfy all the conditions. Okay, so these are the two polynomials that we typically use, but there are other types of profiles, trajectory profiles that we can use. And one of them is called linear segments with parabolic blends, or LSPB, sometimes also called the trapezoidal-velocity profile. So what it is I'm given the initial time and the final time, the initial joint value and the final joint value, and the maximum speed that I want to achieve, okay, or I can achieve. So I'm given these 5 parameters. And what I want to do is to go from my initial speed of 0 to some max speed, then go at constant speed, and then decelerate and go back to 0 speed, okay? So the velocity profile is going to be a bunch of lines. The acceleration is going to be positive, 0, negative. And of course, when you integrate the velocity, so the joint angle is going to be a parabola, a line, and another parabola. That's why you call it the linear segment, which what you can see here. And with 2 parabolas that will blend to it and create the whole profile. So as I said here, I'm given 5 parameters, T naught TF, Q naught QF, and V, which is Q dot max, and I need to find Q as a function of time. Okay, so clearly, as I said, we have 8 coefficients, 3 for each one of the parabolas and 2 for the line, and I have 5 given parameters. I'm not going to be able to calculate all of the unknown coefficients, so we need some extra conditions. And 2 of the conditions that we have here is we start from 0 initial velocity and we go to 0 final velocity. Okay, so these are 2 extra conditions, right, which are very important. So if I want to write this problem, the conditions that I have in general are that Q at T naught is equal to Q naught, Q at T final is equal to QF. These are 2 equations. Q dot at T naught is equal to 0. q dot at t final is equal to 0. This is 4. Then we have continuity conditions, which is basically at this time where you go from parabola to the line, and we call it TB or blend time, which I mentioned for you here. At the blend time, which is an unknown, and we have to determine that, at this T blend, what you have is the value of q from the first function should be the same as the second function. So if I call this portion q1 of t, I call this portion q2 of t, and I call this last portion q3 of t, right? Then what you have is this is q1, this is q3, this is q1, this is q3. Okay, and then continuity conditions will give me q1 at t blend is equal to q2 at t blend. So that's one more condition, and then q2 at t blend is the same as q3 at t blend. So these are the continuity conditions. And also q2 dot at any time should be equal to this v. Remember, I said the maximum velocity we have is called v, and that is this point here. So this point here is v. So I can say q2 dot in general should be equal to what? V, correct? So that gives me the slope of the line, right? That's v. These two, as I said, are continuity conditions. And then I have smoothness conditions, which is basically the slope of the first function q1 at the t blend should be the same as the slope of the second function at t blend. So q1 dot at t blend should be the same as q2 dot at t blend. And then by the way, one correction here. The correction is the next time point that the blending is happening here, this point. This is not t blend, this is t minus t blend, and because the whole thing is symmetric. Okay, so if the left hand side is t blend, the right hand side also this distance should be t blend. So the time point is t final minus t blend. So you have to say q2 at t minus t blend is the same as q3 at t minus t blend. Okay, you need that. And then I have, as I said, q1 dot at t blend is the same as q2 dot at t blend. And q2 dot at t minus t blend is the same as q3 dot at t minus t blend. These two I call smoothness conditions. So far, if you have seen, I have 9 equations, right? 9 equations. What are my unknowns? There are 8 unknowns, the coefficients of q1, q2, and q3, and the t blend, correct? So I have t blend as well as my q1 of t, if you write it as a1 plus b1t plus c1t squared, and q2 of t, you write it as, let's say, d plus e times t, and let me get rid of these ones for here because I don't need them really. and your Q3 is like F plus G times T plus H times T squared. So you see I have 9 unknowns. This is 1, 3 here, 2 here, and 3 here. 9 unknowns, and then I have 9 equations, as you can see. And I should be able to solve the 9 equations with 9 unknowns, which if I do, I will get this criteria for Q1, Q2, and Q3, correct? So this is your Q1, this is your Q2, and this is your Q3, where each one of them is only valid for a specific time period. First one between 0 to time blend, as you can see. The next one is between time blend to T minus time blend, and the last one between T final minus T blend and T final. Okay, now not only you get all of these 8 coefficients, as I said, T blend is one of your unknowns, and you can also solve for T blend, which is going to be Q initial minus Q final plus V T final divided by V. So here are the solution to the 9 equations and 9 unknowns. And if you check them, you see clearly all of those 9 conditions are satisfied, correct? Like, for example, at T of 0 equals 0, here your T naught is equal to 0, okay? At T naught equals 0, you have the value to be equal to Q0 if you plug in TF here in this last one, correct? And simplify, then these 2 negative 1/2 terms with this 1 positive full term would go away. So all of the 3 terms would vanish, simplify together. You'll get your QF. If you look at the slope, Q dot at time T0, clearly this is going to be 0. If you look at the slope, Q dot at time TF, again, you can easily show that it's just these 2 terms that have time derivative. Again, it is going to be 0. So all of these 4 conditions are satisfied. If you look at the middle function, Q2, the derivative of that is V. Clearly, you see it's a linear function, and the slope is V times T, so V is the derivative. So the 5th condition is satisfied. And then clearly, when you plot these functions, you have the smoothness and the continuity conditions. Okay, so everything is basically taken care of, right? So this is the solution. This last one gives you a value for T blend. So when you want to start using this, the first thing you have to calculate is actually T blend. Once you have that, then you can plug it into the first one and the last one. So before you can calculate these coefficients in this Q1, Q2, Q3, first you have to calculate T blend because you need it in Q1 and Q3, as you can see here. Right? Now, here, there is also a limitation on this V max. Okay, this V that you have, V max, it has some limitation. You cannot just choose it to be anything. Because your T blend is bigger than or equal 0, and it is less than or equal T final divided by 2, or less than actually, in general. If you make it equal to, means there is no period of constant V. You directly go up like this, and you directly go down like this, okay? There is no time during which V is constant when T blend is equal to half of T final. When you make it 0, it means literally you're going straight up and then the whole motion is constant. So really, if you want to be realistic, the equalities here are not really appropriate. It has to be less than that and bigger than 0. And so if you now set this to be equal to bigger than 0 and then less than TF, correct? So that formula for TB, if you plug it up here, then it leads to this inequality that you would see here. That your V cannot be anything that you desire. Your V has to be bigger than the delta in Q final minus Q initial divided by T final, and less than or equal 2 times that quantity. So this delta Q over delta T, 1 times that and 2 times that, anywhere between 1 and 2 should be what? Your V. It cannot go like to be 3 times that or 0.5 times that. It has to be between 1 times this delta Q over delta T and 2 times delta Q over delta T. And so that gives you a choice for V, because V, you clearly also see that you have limitations on V, and this V is used in all of the formulas. So before you do that as well, you have to go through this one as well. You have to choose a value for V based on the Q naught, QF, and TF. Then once you have these guys, you can go and determine your criteria, right? And here I wrote a MATLAB code based on these formulas. If you can see here, I have some initial time. You can choose it to be 0 if you want. I have some final time. I have some initial Q, some final Q. Here you see my V. I have chosen it between 1 and 2. I chose it to be 1.5 times delta Q over delta T. T of B is calculated based on the formula you just saw here. And then based on that, I created my Q1, Q2, and Q3, which here I called actually temp1, temp2, and temp3. And then the combination of them I called what? Q. Okay? So if I want, instead of temp1, I can call it Q1, right? So it's not a big deal. Or I can call this one Q2. And I can call this one what? Q3. So I form my total Q. I calculate my Q dot and Q double dot using numerical differentiation. And then what? I can plot it for you. Okay, here is the result. As you can see, the joint variable is basically a parabola, as you can see, then followed by a line and then another parabola, right? So it is a linear segment in the middle with 2 parabolas on the ends. It's blended with them, so we call it LSPB. Or if you look at the velocity profile, you clearly see it is a trapezoid. And also if you look at the acceleration, you see the step type behavior. It jumps from a positive number to 0 to negative, okay? So this is our LSPB or trapezoidal motion that you can see. And the main problem with this type of motion is this jump in the acceleration. When you have a step type jump in the acceleration, the derivative of the acceleration that, if you remember, we called jerk, and it shows the sudden changes in the forces, right? It shows, it's an indication of impact basically in your system. If you have that and calculate it, so jerk is equal to d of q double dot, right? The joint accelerations over time. If you plot it, so let's say here, for example, at any point it is going to be 0, but when you have those sudden jumps, so if this is t, this is j, you see it is going to be like 0, then 0, and then 0, and then here you have a big spike and another big spike. And these are kind of like impacts that are acting on the actuator and on the links of the robot, and those are going to affect the useful life of the robot, and they are going to make the motion non-smooth in general. You see jerky kind of behavior. So large jerks is not a good idea. That's why there is another version of this trapezoidal velocity motion that is a little bit modified, and what you do, you try to get rid of these sharp corners in the velocity and as well here. So you go with the parabola here, a line, another parabola, straight line, parabola, then you go straight line, and then again you go with what? Another parabola. Okay, so this kind of smooth version of this trapezoid is what we call S-curve, which you can see here. So if you plot the joint velocity versus time, it is a trapezoid, but at the sharp points you have what? You have a rounded feature, which means it's not going to be constant acceleration all the way from beginning to where the velocity is constant, just like here, right? If you compare, you see here you have constant acceleration, zero acceleration, constant acceleration, as you can see. Here it's different. Here you have variable acceleration or constant jerk. So here jerk is constant, but acceleration is a linear function of time. And then you have constant acceleration. Again, you have jerk, but negative jerk this time, so acceleration is decreasing. It's basically gonna go down until it goes zero here, and then here it drops. So if you look at the profiles for velocity, acceleration, and jerk, these are the four plots that you see. The green one is that modified trapezoid or S-curve that we mentioned. If you look at the acceleration, you go up linearly, then you stay constant, then you go down linearly to zero, then you stay at zero, and then exactly the opposite of that. You go negative, you go constant negative, and then what? This is where you're dropping your velocity, and then you go to zero. Okay, so you start at zero velocity and you end up with zero velocity. The same thing with acceleration. You start with zero acceleration, you end up with zero acceleration, correct? So you start from rest and go to rest, basically. Your start angle can be zero or non-zero, and your final angle is whatever you want to rotate. And if you look at the jerks now, you have some positive jerk, zero jerk, negative jerk, zero jerk, negative, zero, and positive jerk. So the motion consists of 7 separate parts, despite the previous one being just 3 parts, if you remember, right? You had part 1 between 0 to t blend, between t blend to t minus t blend, t final minus t blend, and between t finus minus t blend and t final. So you only had 3 segments. Now your motion has 7 parts. So that's another name that they call it a 7-segment profile. Okay, and here I'm going to show you a formulation for that as well, which I derived. So what I will do here is I assume a general cubic form for the joint variable, which means a quadratic form for the joint velocity, which means a linear form for joint acceleration, and which means a constant number for the jerk. Okay, now in some cases the jerk is 0, like between t1 and 2, between 3 and 4, and between 5 and 6. For all of these cases, jerk is 0. For some cases the acceleration is also 0, like between t3 and t4. Okay, velocity is never 0, but in one range it is constant, and that is between t3 and t4. Okay, so some of these A's or B's could be 0. As I said, 3 of the A's that I guess I mentioned them in my notation. If you look, you have your A2, 4, and 6. All 3 of these are 0, and among B's is only B4, the middle B, the B for the middle motion between 3 to 4. That is 0. The C's are not 0. Now we start from 0 velocity and 0 what? Acceleration. What does that mean? it means B1 is also 0, right? The acceleration term for the constant of the acceleration term for the first motion. That's your initial condition. It has to be 0 in addition to B4. So not only B4 is 0, B1 is also 0 because we chose to start with 0 acceleration. Your initial velocity, we assume it's 0. That means C1 is 0 and your Q initial is 0. Now you don't have to choose your initial angle to be 0, but since you can measure everything from the Q initial, you can, for simplicity, assume that the Q initial is also 0. Q final is definitely not. That's the angle you want to rotate through. The final time here, we show it with capital T. The initial time is 0. Now, what you consider here is 3 constants. One is the maximum velocity, just like the previous case, correct? This Vmax, this is the maximum, the fastest that your motor or linear actuator can move or rotate. You also have some maximum acceleration, which you can see here. This is your Amax, right? Which comes from your motors again, how much torque they can generate or how much force they can generate. And you also have another parameter to choose, and that is maximum jerk, right? How much jerk your system can tolerate, how much impact can it tolerate without mechanically failing. So Vmax and Amax comes from your actuators, Jmax comes from your physical system, really. Okay, so here you choose the 3 parameters, Amax, Jmax, and Vmax. And based on that, you can easily find the criteria for each one of the Qs. In general, here you have 7 Qs, right? You have Q1, Q2, Q3, Q4, Q5, Q6, and Q7. And each one of these Qs, as you can see, it has 4 coefficients, A, B, C, and D. So you have 7 times 4, that's 28. There are 28 coefficients to find, and also you have to decide about the time T1, T2, and T3, okay? You have to find them as well. And I'll show you not only that, you actually need to also find your final time as well. So there are in general 32 unknowns here, but don't worry, I've gone through all of them, and I solved this 32 unknown, 32 coefficients. Wasn't easy, but I did it, and here I can show you. If you choose your Vmax, Amax, and Jmax, as I said, and your Q final, these are the 4 parameters that you have to choose. As I said, based on the motor, these 2. This is based on the mechanical properties of the robot link, and QF is the angle you want to rotate through. Okay, so you have 4 given numbers. Your initial time is 0, of course, in this case. You assume the initial velocity and acceleration to also be 0, and the initial angle. And then what you can do is you can determine your final time. Your final time can be given by this formula, Amax over Jmax plus Vmax over Amax plus QF over Vmax. Your T1 time comes from Amax over Jmax. Your T3 is going to be Amax over Jmax plus Vmax over Amax, and it has to be less than T over 2. So if you choose this Amax, Jmax, Vmax such that this T3 that you get from this formula is equal or bigger than half of this T that you found from the top one, you cannot achieve such motion. Then the rest of the times you can easily find. So T2 is T3 minus T1, T4 is T minus T3, T5 is T minus T2, T6 is T minus T1, and that's all coming from symmetry here. So if you look all of this motion, except for Q, the rest of the parameters, V, A, and J, they are all symmetric about the middle point. So if you can draw the middle point here, a line like this, the V profile, the A profile, and the J profile. The A profile is not symmetric about the line, it's symmetric about the middle point. V profile and J profile, they are symmetric about what? they're symmetric about the line, but the A profile is symmetric about the point. So when you reverse it, when you mirror that from the left side to the right side, you have to also negate it. Q is not perfectly symmetric, okay? Unless you have your initial Q to be the negative of the final Q, then yes, you might get that also symmetric, again, about the middle point. So using that, you can say, for example, whatever distance I have here, I also have here. That's why if this is T1 from T1 to 0, then the last one should also be T1. So it means T6 plus T1 is T final or cap T. So T6 is what? T minus T1, right? Or if this is like from here to here all the way is T2, which is the same as this one. So it means T5 plus T2 is again cap T, so T5 is cap T minus T2. So that's where these formulas are coming from. Okay, and now your coefficients, the A's, can all be given based on the J values, because you see the J's are all constant. So J in the first motion and the last part of the motion are positive J max, and then we consider in the third and fifth part of the motion to be negative J max. Okay, and these are for simplicity. You don't have to choose the positive value and negative of J value to be necessarily the max. One of them can be less than the max in terms of magnitude. But here, to make it as symmetric as possible and make the calculations as simple as possible, we choose to go with max jerk in parts 1, 3, 5, and 7. As I said, then A, 6, 2, 4 are all 0. And these are all of your A's. So if you see here, I have given you all of your A's. You can start with these A's. Out of your B's, B4 is 0. That's given to you. B1 is also 0 because your initial acceleration is 0. And your B2 and B6 are equal to A max and negative A max. And that comes from this plot here. This is the B2 value, and this is the B6 value, the accelerations in second and sixth part. And they are equal to A max, as you can see here, and here this is negative A max, which you can see. So you have, if you can see, you have 4 of your B's, correct? You have 4 of your B's. Your C4 is also the velocity in the center part, and that is your Vmax, correct? So we know that one as well. So if we project that here, this guy is also Vmax, right? So the velocity also for the center portion is Vmax, so that is equal to C number 4. Okay, so your C number 4 is given, also C number 1 is given because that's the initial velocity. And since the initial angle is 0, it means D1 is given. So out of these 7 times 4, out of the 28 coefficients that we have, several of them are given here. And the rest of them, which you can see over here, these guys you have to find, which are about 14 of them. Okay, so 14 coefficients you have to find, but it's not at all hard. I'll show you. First of all, 14 left. Why 14? And do I have enough equation to get it? Well, A's are all gone, and some B's and some D's and BCDs are gone. So 14 are left, but do I have enough equation? Well, the matter of fact is yes, I do. At each one of these intersection points, which is T1, T2, T3, T4, T5, and T6, not only the Q's should have the same number, the Q dots should have the same number, as you can see, because your Q dot is a smooth function, and your Q double dots, or A's, should have the same number because you see it's a continuous function. Okay, so at t equal ti, where I is from 1 all the way to 6. Okay, it's not the first one, it's not the last one. At each t equal ti, I should have 3 conditions. Qi at that ti should be the same as Qi plus 1 at that ti. It's the continuity in Q. And then for smoothness at that point, I should have Qi dot at ti is equal to Qi plus 1 dot at ti, and then Q double dot I at ti should be the same as Q double dot I plus 1 at that ti. Okay, and you might say, well, how many conditions are these? Well, there are 3 of them and there are 6 points, so it's 18 conditions. These are 18 conditions. But you might say, well, I only have 14 parameters. If I have 14 parameters to find here and I have 18 conditions, will I somewhere get into problem because I have more equations than unknowns? And the answer is no. If you here take a look, I have 4 formulas for you for capital T, T1, T2, and T3, which you can see here, these 4 guys in blue. These 4 formulas come from those 4 extra equations that you have. Okay, so the fact that I could calculate these formulas, they are from the continuity conditions. So as a matter of fact, you have 18 unknowns, 14 coefficients plus 4 time values, T1, T2, T3, and cap T. And now you have 18 conditions. From these 18 conditions, you should be able to find all of these guys. And all of these. Okay, so you might say, well, how? Let me show you, for example, where I got some of these. For example, where did I get T1 equal A max over J max? Because I don't want to just give you formula, I want to show you how you can handle this by yourself. So A max over J max is T1. Well, that comes from the first part of the graph. If you see, time goes from 0 to T1. Let me get rid of these. Your time goes from 0 to T1 in the first part of the motion, correct? And then with the constant jerk of J max, you go from acceleration 0 to acceleration A max. And since the relation for the acceleration is linear, clearly this A max, the height, is equal to the slope. This J max here is the slope of the line times the time that you had, which is T1. So you see, T1 J max is equal to A max. So from here, T1 is what? It is A max divided by J max. Correct? Which you can see over here. Right? Where does the other formula come from? T3, for example. T3 comes from what? Well, for T3, let's go take a look. T3 is the end of the third part, which is you go through one full trapezoid of acceleration, as you can see. Or during this full trapezoid, which goes from 0 to T3, you go from 0 speed to what? To the Vmax speed. Correct? This is what? Vmax. So your speed changes from 0 to Vmax, and that's because of this profile trapezoid of acceleration. And you know the change in V, or delta V in general, which is Vmax minus 0, delta V is equal to what? integral of a dt. The integral of a dt means the area under the curve of a versus time. So it's the area of this trapezoid. And how much is it? You know, the area of a trapezoid is the average of the two base times height. Well, the bottom base is T3. The top base is T2 minus T1. The average of these two. And then times the height, which is what? A max. Correct? So this is the formula you have. Now, before I can solve this for T3, I need another relation, which I have over here. And that is T2 is equal to T3 minus T1. Where do I get this one from? Well, that comes from the fact that your acceleration goes from what? 0 to 0 during this trapezoidal motion. And you know the change in acceleration during the very same time between 0 to T3, the change in acceleration, as you know, which is 0 minus 0, correct? Final value minus initial value, comes from the integral under the area of the jerk, which is this area here in green. And what is this area? Well, it is T1 times J max and plus what? Or minus, actually, minus T3 minus T2 times J max, correct? Because if you remember, if this is positive J max, I said this value here is what? Negative J max. I don't have to choose it that way, but if you do, it makes life a lot easier, makes your formulas a lot better. So clearly from here, you see what? Since it's 0, from here, your T1 has to be the same as T3 minus T2. And from here, clearly your T2 is what? T3 minus T1. So that's where I got this formula from. Now that I know T2, I plug it into this bottom top formula. So T2 is T3 minus T1. So now if you look, you have two T3s, negative two T1s divided by 2. So this whole thing can be simply simplified as T3 minus T1 times A max is V max. Therefore, your T3 is going to be V max divided by A max. And then what? Plus T1. Take T1 to the other side. Right? And that is this formula here. Well, let's see. I said A max divided by V max divided by A max plus T1. But T1 itself, if you remember, T1 is what? A max over J max. So I just replaced it. And that's this formula. So you see how I got these three formulas for T1, T2, and T3? Yes? So I'm using continuity conditions and the fact that I should go from one area to another. Now, what is the last one? This formula for capital T, where does that come from? Well, that comes from the change in the angle. You go from initial angle that we chose to be 0, unlike this case where it starts from a negative Q. We start from 0 Q and go all the way to some Q final. And the change in the angle is area under the curve of what? Under the curve of velocity. Right? So if I can find the area under the velocity curve, that is Q final minus Q initial. Now, how can I do that? So to do that, I need to do a little bit of cleanup, if you don't mind, because it's just too crazy here. So I will do just very fast cleaning here so you can see when I'm plotting something for you. Okay, good. Now what? Now what's the area under the green curve? So it is actually a trapezoid, but you have to pay attention. So what I will do, I will connect this point where the linear velocity, the constant velocity start to the beginning, and I also connect the end of the point T4 to T7. If I connect them with two lines, let me see if I can connect them for you. Okay. There we go. This is one, and this is the other one. Okay, because of the symmetry, the area of this between the green line and the black, the green curve and the black line, which is this area here. So this area is where the line is bigger than the green curve. This area here, let me use a different color. This area here in red is where the green curve is bigger than the line. But because of symmetry, the green area is exactly the same as the black area. And similarly here, if I do the same thing, here in the blue area, again, the velocity is bigger than this, the actual velocity curve is bigger than the black lines. And here in the T5 to T, or kind of, yeah, it's at T5, I guess, to T7, you have the line to be bigger than the actual velocity profile. But again, the blue and the green areas are the same. So the area under the trapezoid, really, the area under this trapezoid is the exact same thing as the area under the actual velocity, v. And what is this area? Well, the area here, which is, as I said, area under velocity, and it's equal to q final minus q initial. By the way, your q initial here, I assume 0, but you can choose it to be non-zero. This is equal to what? The area of a trapezoid, which is the big base, which is capital T, plus the middle one, which is T4 minus T3, divided by 2, and then times the height, and the height is V max. Correct? You know, this area here is, this is V max. But if you remember, T4 is T minus T3, right? Where is it? Here. T4 is T minus T3. Therefore, I can replace it up there. So let's go ahead and replace it. Just trying to do a little bit of cleanup. I just made it too busy here. So if I replace it, this is going to be T minus T3. And now if you look, again, you have 2 cap T's minus 2 T3s divided by 2. So this whole thing can be written simply as T minus T3. Right? And from here, you see your T is going to be Q final over V max, and then plus T3. And T3, if you replace it from what we had in the past, this is T3, and this is that Q final over V max, which you found here. Correct? So it exactly gives you what you wanted. Right? So you see, I'm using these continuity conditions, and that gives me the value for this 4 time points. Now that I got my 4 time points out of those 18 equations that I had up here, 4 of them are gone. I'm down to 14, and guess what? I have 14 coefficients here to find, and it's just coming from those equality conditions, right? The Q's are the same, Q dots are the same, Q double dots are the same at the share points, intersection points. And here, if we go and look at my MATLAB code, I'm using the same thing here. So when I have my A's and my B's, when I want to calculate my C's, let's say, or D's, I'm just calculating the value of Qi at the Ti subtracted from Qi plus 1 at the Ti, except for the parameter that I'm trying to choose, and then that gives me the unknown. So if you bring this whole thing, for example, if you bring this whole thing to this side and add it to C2, it means exactly what? It means that Q1 dot at T1 is the same as Q2 dot at T1. If you look at this, this is going to be Q3 dot at T2 is the same as Q2 dot at T2. And since everything here is known through these recursive equations, I can get all of my C's, all of my D's that are missing. My A's and B's are good. And here I have 7 parts of the segment. So I need to divide my whole time point into 7 areas, which falls within one of the ranges. And then when I form my Q's based on those cubic formulas, where some of the coefficients are 0, then because I have those indexes, I can limit the data in Q1 to only the Q1 where T falls in this region. So I say Q1 of index 1. The same thing I do for velocity, for acceleration, and for jerk. And here, if I run this for you, so here you see I wrote a bunch of code. I started from, you see, line 141 and it went to 256. With the spaces, it's probably around 120 lines of code. But here, if I run it for you, you can see the result. Right? So you see constant jerk, 0 jerk, constant jerk, 0 jerk, constant jerk, 0 jerk, positive jerk, max. Here your jerk max is 12, and you can see the number here is 12 also. Then your max velocity is 3, and your max acceleration is 3, max velocity is 2. So you see your max velocity is 2, your max acceleration is 3. You see, in linear increase, constant, linear decrease, constant, linear decrease, constant, linear increase. Go back to 0. This is your nice S-curve for velocity. And finally, this is your Q going from Q initial, which is 0, all the way to Q final, which is, in this case, 150 degrees, right? Q final. And if I calculate my Q final here, it is 2.61, and that is the number that you see that this one converts to, 2.61. Okay, so it is working perfectly fine. Again, we call this S-curve because of the shape of the velocity, or we call it 7 segment because it has 7 parts going from T0 to T1 all the way to T6 to T7. There are 7 parts of the motion. Okay, so this is a good choice for robotics applications, right? Where you can start from 0, go to some constant velocity, stay there, and then smoothly go back to 0 and travel from initial angle to final angle without you exceeding the maximum RPM that your joint can rotate, without you exceeding the maximum acceleration or the maximum torque that it can generate, and without you exceeding the maximum jerk that the mechanical system can withstand. So this one is the best one, actually, I would say. Of course, you see calculations are a lot more. Instead of just 4 numbers here or 5, 6 numbers here, or in this case, in general, you have like 9 numbers, correct? If you remember here, you had 8 coefficients plus T, B, and you have to have some limitations on B, right? Then instead of 9 parameters here, if you remember, in this case, I have 32 parameters, 28 coefficients plus 4 time values. And here I have derived all of them for you. So hopefully now you know how to generate trajectory of your choice, so that you can have everything under control, right? Here you have everything under control, A under control, V under control, jerk under control, and go from Q0 to Q final. Unlike these other cases, you don't have very large jerks, you don't have very large accelerations or very large what? Velocities that your system cannot handle, right? So this is the best option. You have to do some computation, but as long as you know how to use continuity conditions, running it and creating it is not the hardest thing in the world. Okay, thank you so much for your attention. See you in my next lecture.